Welcome, focused learners, to today's explainer. I am absolutely thrilled to get into this one, because today we're going to demystify what honestly feels like an impenetrable alphabet soup of AI databases. You know, when we read about artificial intelligence, it is just so easy to get totally lost in the buzzwords. But today, we're looking exactly at how these systems physically function under the hood. We're going to break down this incredibly complex data architecture into clear, understandable components. So let's just jump right in.
Now, there's a quote that perfectly shatters a really common illusion. It goes, "In the modern AI ecosystem, no single database system handles every aspect of the data lifecycle." See, we often think of an AI as just a single magical software brain, right? Like a monolithic black box that just somehow knows things. But the reality? It's a highly orchestrated symphony of completely distinct data engines. There's literally no single system that does it all.
So here is our roadmap for today. We'll start with the AI database ecosystem, move into vectors for semantic search, then tensors as the GPU heavy lifters. After that, analytics and open storage layers, the role of traditional SQL, and finally we'll bring it all together with the complete AI stack.
Section 1, the AI database ecosystem. Let's meet our team of specialists.
Section 2, Vectors, Semantic Search and Context.
Building real-world AI applications is a massive logistical challenge. Think about it. You have to manage unstructured raw media, process high-dimensional math, and feed incredibly fast GPU training pipelines all at once. It absolutely demands a highly specialized team. So to understand our first specialist, vector databases, we first have to understand what they actually store, and that is 1D vector embeddings. These are numerical arrays generated by AI models. Whether you feed the model text, an image, or a piece of audio, the AI translates that raw, unstructured data into a one-dimensional array of numbers. I always find this just fascinating. It's quite literally translating human meaning and concepts into a mathematical format that a machine can easily process and compare.
But what's really wild is how we actually use those vectors. The primary job of a vector database is not your traditional exact keyword matching. Instead, it performs incredibly fast similarity searches using mathematical distance metrics. You might hear terms like cosine similarity or Euclidean distance. Basically, the database plots these vectors in mathematical space and locates the nearest neighbors, often called KNN. It's finding mathematical proximity to locate items that are semantically related to each other, even if they don't share the exact same words.
To ground all this abstract math in reality, where do we actually use this stuff? Well, the biggest use case right now is Retrieval Augmented Generation, or RAG, for large language models. When you ask a chatbot a question and it instantly searches a company handbook to give you a highly customized answer, that is RAG powered by a vector database. They also run semantic search and recommendation engines. Some real-world examples you might run into include Pinecone, Qdrant, and Milvus. Actually, you can even find vector extensions integrated right into analytical SQL engines these days, like DuckDB's VSDs extension.
Section 3. Tensors, the GPU heavy lifters. Let's see how this builds.
Okay, so if vectors are the semantic searchers, tensors are the absolute heavy lifters of the GPU training world. Deep learning models require an incredibly complex level of mathematical processing that goes way, way beyond just a simple list of numbers. Enter ND tensors. These are n-dimensional arrays. We're talking 2D, 3D, 4D, or even higher dimensional spaces. These dense and sparse arrays are absolutely required to represent rich media like images, audio, and video, as well as the attention matrices and complex neural network weights that actually make deep learning function in the first place.
To make this perfectly clear, think about the structural contrast here. A vector database deals with a simple 1D array. Think of it like a single, straight line of numbers. But a tensor database manages a multi-dimensional ND array. It's more like a complex, multi-layered Rubik's Cube. It's highly spatial, it has multiple axes, and it requires a completely different type of database architecture to store and slice that data efficiently.
Because of this massive structural difference, tensor databases have a very specific primary function. They excel at high-throughput multidimensional slicing and linear algebra transforms. Basically, their main job is to stream massive amounts of raw, multidimensional data directly into training frameworks like PyTorch or TensorFlow. And, crucially, they do this without slowing down the GPU. They literally eliminate the disk bottlenecks that would otherwise completely cripple a multi-million-dollar model training run.
The real-world applications for this are just amazing. Tensor databases are the backbone for training pipelines in LLMs and computer vision.
They're used to process complex, multi-layered data like 3D medical MRI and CT scans, or massive geospatial satellite imagery. When you hear about tools doing this kind of heavy lifting at scale, you're looking at systems like ActiveLoop Deep Lake, which is often known as the Tensor Database for AI, as well as TileDB and Google TensorStore.
Section 4. Analytics and Open Storage Layers.
Now that we've covered the really specialized math engines, we need to drop down to the foundational layers of the stack. This is where we combine the logical context engines with the massive data archives. First up in this layer are the analytical engines and cloud warehouses. While our previous databases handled embeddings and tensors, these engines manage the structured business records, the metadata catalogs, and the contextual domain data. They execute high-speed SQL analytics across tabular data. But here is the most fascinating part. Modern analytical platforms now feature integrations like the Model Context Protocol, or MCP. This brilliantly allows AI agents and LLMs to query structured warehouse datasets directly using plain natural language. Key players here include DuckDB, MotherDuck, Snowflake, and Google BigQuery.
And supporting all of this, at the very bottom, are the open lakehouse catalogs and object stores. Think of this as the massive persistent archive. They pair low-cost cloud object storage, like AWS S3 or Cloudflare R2, with open columnar file formats, specifically Apache Parquet. This setup allows you to store absolutely enormous AI datasets cost-effectively, while still maintaining sub-10 millisecond metadata indexing and schema-wide multi-table ACID transactions. Solutions like Duck Lake, Apache Iceberg, and Delta Lake are exactly what make this unified, long-term storage possible.
Section 5. The role of traditional SQL. The anchors of exact operational logic.
So you might be wondering, with all this incredible new AI technology, what happens to the traditional databases we've used for decades? Well, the distinction here is absolutely crucial. Unlike an AI vector search that looks for nearest neighbors and conceptual similarity, standard relational databases are strictly for exact operational lookup logic. If you are searching for user ID number 459, you definitely don't want a conceptually similar user, right? You want exactly user 459.
Because of this, traditional SQL databases still have absolutely vital everyday tasks. They manage the core application transactional state, they handle exact keyword lookups, your standard where queries, they manage user accounts, system logging, and they even act as the metadata backends for those massive lakehouse catalogs we just talked about. These are the battle-tested, workhorse tools you already know and love, like Postgres, MySQL, and SQLite. They aren't going anywhere. They just have a very specific structural role in the wider orchestra.
Section 6. The complete AI stack, bringing it all into a unified architecture.
All right, it is time for the grand finale. Think about how beautifully specialized this unified stack really is. You have your vector databases handling 1D embeddings for semantic search. You have your tensor databases slicing ND arrays for GPU training. Your analytical engines are leveraging structured Parquet files and hybrid SQL to give your AI agents actual business context. Your open lakehouses are acting as the low-cost, persistent storage for massive datasets. And finally, your relational SQL databases are managing structured tables for exact keyword lookups and transactional state. Every single component has a primary data format, a specific query logic, and an indispensable role in making modern AI actually work.
I want to leave you with a provocative thought to chew on. If modern AI is actually an orchestrated symphony of distinct data engines, rather than a single magical brain, how does that change the way we build the applications of the future? Because we are no longer just writing software, we are conducting a highly complex orchestra of vectors, tensors, and structured logic. I really hope this explainer has given you the structural clarity to see exactly how these incredible systems are built from the ground up. Thank you so much for diving into the anatomy of the AI ecosystem with me today. Keep learning and keep building.